Hey, welcome to C Programming. Today's lecture, we have two topics we're going to be covering. The first one is on number bases, and then we're going to cover how you can read input from a user. So to start off, we're going to talk about number bases. There are a number of different number bases that we use. The primary one is base 10. This is also known as decimal. This is how we all learned to count. Although most of us probably learned to count from the number 1 rather than the number 0, in base 10 there are 10 different digits that we use, which are from 0 through 9. When we get up past 9, we then have to use 2 digits to represent any number, and you learned somewhere back in elementary school probably that the second digit would be the tens place, and then the third digit would be the hundreds place, and the fourth digit would be the thousands place. If you didn't realize, what you're doing at each one of those digits is you are raising the number 10 to an exponent. So the ones place is the 10 to the zeros, the tens place is the 10 to the 1, the hundreds place is the 10 to the 2, thousands place is the 10 to the 3, and so on. We have other number bases that we use also to represent numbers either smaller or larger. The next one we'll talk about today is going to be base 16. This is the hexadecimal number base. This allows us to represent all of the numbers from 0 up through 15 with just a single digit. Now, since our numeric system that we have only consists of the digits from 0 through 9, we had to come up with some other character to use for 10 through 15. So that we can keep these still as a single digit, though, we use the letters A through F, where A represents the number 10, B 11, C 12, D 13, E 14, and F represents the number 15. So in hexadecimal, which is base 16, there are the numbers from 0 through 9 and then A through F, and that represents the numbers between 0 and 15. So with base 16, what we're able to do is we're able to represent up to the number 15 with just a single number, a single character. So the number 15 would be an F. So the first digit that we have in a hexadecimal value would be the 16 to the zeros digit, which would be the ones. Then the second one would be the 16 to the 1, which would be the 16th place, similar to how we have with decimal. We'll do some conversions in a second, so you'll see a little bit more on how we use this. One reason that we have hexadecimal, we don't just use decimal for everything. Hexadecimal, first of all, is a power of 2. And we've learned that inside of a computer system, almost everything that we do is in binary, which is base 2. And you see that one down at the bottom of this slide here. So whenever we have something which is in power of 2, it simplifies conversions for us because we can easily convert to binary from hexadecimal much easier than we can do with decimal to binary, let's say. There are ways to do it. I'll show you the algorithm that we use to go about converting from one number base to another, but whenever we're dealing with anything which is a base 2 or a power of 2, it's going to make it a lot easier for dealing with computers, since we do everything with zeros and ones. So let me jump down to the bottom one right there, base 2, which is binary. You see that we have the digits 0 and 1 because the first place is the 2 to the zeros place, that's the ones, and then the next place is the 2 to the 1, which gives us the 2s, and the next one would be the 2 to the 2, which would be the 4s place. So with binary, we only have the digits 0 and 1. The word bit, little historical fact here, the word bit comes from a binary digit. So we take the BI from the word binary, we take the T and the S from digits, and we push those together and we get the word bit. So 1 bit is just one binary digit. 8 bits makes a byte, and whoever came up with byte apparently was had a little too much time on their hands, and they decided they would come up with a word for 4 bits also. And if anyone doesn't know this, you can go ahead and Google that and find out that 4 bits is called a nibble. Okay, the other number system that I have there, base 8, is octal. It has the digits from 0 through 7, and the first bit would be the 8 to the zeros place, which is the ones. The second would be the 8 to the ones, which is the 8s, and then the 8 to the 2, which is the 64s, and so on. Jumping back up to hexadecimal, and another reason why we would use hexadecimal over decimal is because we can represent larger numbers with fewer characters. So if we wanted to represent a very, very large number, we can do it in hexadecimal, and it would be fewer digits than it would take for us to do it in decimal. One place that we use hexadecimal, for any of you who have done any HTML programming or dealt with any color coding in computers, we usually use hexadecimal for that, because we would have the RGB, the red, the green, and the blue. Each one of those can be represented by up to 256 different values. And if you do decimal, base 10, obviously the number 255 has 3 digits, but in hexadecimal we can represent up to 255 with just 2 hexadecimal values. And so we can knock off one character from the red, one character from the green, and one character from the blue. So instead of having to have 9 characters to represent the RGB value of a color in base 10, we can just have 6 characters represent the RGB value using hexadecimal. Okay, so let's start off. Here's our first conversion. How would we convert from base 10 to base 2? The way that we convert is that we start off with our number. So the number that we're going to try to convert from base 10 is the number 201. And we want to find out what the binary equivalent of the base 10 value 201 is. What we do is we just start dividing by 2 and take the quotient, find the remainder, and we are going to just write down all of the remainders. So we do 201 divided by 2, we get 100 as the quotient with a remainder of 1. And then we're going to take our quotient of 100 and divide that by 2. We get 50 with a remainder of 0. Take our quotient 50, divide that by 2, we get 25 with a remainder of 0. 25 divided by 2 gives us 12 with a remainder of 1. 12 divided by 2, 6 with a remainder of 0. Continuing, 6 divided by 2 gives us 3 with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. 1 divided by 2 gives us a 0 as our quotient with a remainder of 1. As soon as we get to 0 as our quotient, that's when we stop. From this point, we are going to copy the remainders from the bottom to the top. So we write down 1, 1, 0, 0, 1, 0, 0, 1. You see that I've done that right here? 1, 1, 0, 0, 1, 0, 0, 1. So we copy those numbers down there. That becomes our base 2 equivalent of our number 201 in base 10. Most calculators that you have on computers also have the way that you can convert this. You can verify that this is correct by doing that. I'm going to just run our Windows calculator here. If you go over to the programmer side, so I selected view and I went to programmer, and you see right now I'm on decimal, so I'm going to type in the number 201, and you can see right here it automatically converts it for me. You can see all of the bits, 1100, 1001, so it converted it correctly. If you want to see it in a little bit bigger up here, just click on the binary and then it'll show it to you up there. So you can see that we converted our number 201 to binary correctly. We verified it here in our Windows calculator. Other operating systems calculators will do the same thing, and what you're going to see also is that the program that we're going to write as part of today's lecture is we'll actually perform the conversion ourselves and write a program to do the conversion for us. Okay, now we're going to look at how we convert from base 10 to base 16. So this is going to go from decimal to hexadecimal. We just saw converting it from base 10 to base 2. We just divided by 2 and copied the remainders. It works exactly the same way converting from base 10 to base 16. So let's take a base 10 number, 199, and we're just going to start dividing it by 16 since we want to convert this to hexadecimal. So we divide it by 16, we get a 12 with a remainder of 7. We then take our quotient of 12, divide that by 16, we get a 0 with a remainder of 12. As soon as we get a quotient of 0, we stop dividing, and we're just going to copy up from the remainders. So the first remainder we had was a 12. 12 in hexadecimal is going to be the character C, and then 7 is just the character 7. So 199 in base 10 is going to be C7 in base 16. If you want to verify that again, we can do that with the Windows calculator. So back on the programmer view, decimal, I will type in 199, and then we have this button here for hexadecimal. Click that, and you see that it converts it to the hexadecimal value C7. Okay, now let's look at 4045 base 10. We're going to convert that to base 16. So I start by dividing it by 16. I get 252 with a remainder of 13. I then take 252 divided by 16 to get a 15 with a remainder of 12. And then 15 divided by 16 gives me a 0 with a remainder of 15. I start copying up from the remainders from the bottom because I had a 0 as my quotient. So it's going to be 15 in hexadecimal is the letter F, 12 in hexadecimal is the letter C, and 13 in hexadecimal is the letter D. So you see that my hexadecimal number is going to be FCD, and that will be the decimal number 4045. So it took us 4 characters to write it in base 10, and it only took us 3 characters to write it in base 16. Okay, going from base 2 to base 10. So base 2 means that we have a bit string that only has zeros and ones. So here's my bit string 10011. This is the language that computers actually understand. Everything inside of a computer is based on bits, high, low, on, off. That's what the ones and the zeros represent. If we get down to the electrical engineering level, then those the logical 1 and the logical 0 actually represent different voltage levels that we have inside of a computer. So let's say that we have voltage levels between 0 volts and 5 volts, then that would mean that a logical 1 would probably be something above a 2.8 volts. Maybe that would be a threshold. So above 2.8 volts, we would say that's a logical 1, and if we're below 2.2 volts, let's say, that would be a logical 0. If we're somewhere in the middle, that means that we may have had a little bit of signal attenuation, and we don't want to necessarily conclude that we had a logical 1 or a logical 0 because the signal may have been boosted or it may have been dropped a little bit. So we put that into a state that we just say we don't know, it's not a strong enough signal, maybe we need to retransmit that signal. But that is how we get these logical values, these binary values from these electrical signals that we have inside of computers. It's all just based on the voltage levels that we have, and based on the voltage level, we then associate that with either a logical 0 or a logical 1. Back to our conversion. So we are going to take each one of these bits. We're going to start with the low order bit. That would be on the right hand side because this is the 2 to the 0's place. So this 1 right here represents the 2 to the 0. So you see I have a 1 times 2 to the 0. This 1 right here represents the 2 to the 1. So there's my 1 times 2 to the 1. I'm going to add that to a 0 times 2 to the 2 right here. Add that to a 0 times 2 to the 3. And add that to a 1 times 2 to the 4. So what that's going to give me is a 1 times 2 to the 0 gives me a 1, 1 times 2 to the 1 gives me a 2, 0 times 2 to the 2 gives me a 0, 0 times 2 to the 3 gives me a 0, and 1 times 2 to the 4 gives me a 16. We add all of those up, we get 16, 17, 18, 19, and that becomes my base 10 number from 10011. If we want to check this out again on our calculator, we can start off with our binary, so we can click on this little button here for binary. Let's type in 10011, convert that to decimal, click the decimal button, and you see that it converts it to 19 base 10. Okay, next let's convert base 16 to base 10. It's a very similar analogy to how we just did the base 2 to base 10, except instead we have these numbers are represented. The first place is the 16 to the 0's place, the second place is the 16 to the 1's place, and the third place is the 16 to the 2's place. So you see that I have the number 3A7 in hexadecimal. So that's going to be 7 times 16 to the 0, add that to 10, which is our letter A, 10 times 16 to the 1, add that to 3 times 16 to the 2. I copied down right below here, 16 to the 0 is a 1, 16 to the 1 is a 16, and 16 to the 2 is 256. Multiply those out, I get a 7 plus 160 plus 768. We add those up, and you get 935. Let's go ahead and verify that. So come to our hexadecimal button on our calculator, type in 3A7, click the decimal button, and you see that it converts it to the base 10 number 935. Alright, our last conversion that we're going to go through is how do we convert from base 16 to base 2. I told you that this is a very easy conversion to do. We like going from these different powers of 2, and here's the reason. With base 16, each one of these hexadecimal digits that we have is represented by 4 binary digits. So all we have to do is say a C in base 16 was a 12. 12 in binary is 1100. This is the 1s, the 2s, the 4s, and the 8s. When we add an 8 and a 4 together, we get 12. So C in base 16 is 1100 in base 2. 2 in base 16 is 0010 in base 2, and D in base 16, which is 13, is 1101 base 2. All we do then is take those numbers, write them in the exact same order that they were in the hexadecimal number. So we write the C, 1100, we write the 2, 0010, we write the D, 1101. And that converts our hexadecimal to binary. If we were converting octal to binary, which is base 8 to base 2, instead of having each octal digit represented by 4 binary digits, it would be represented by 3 binary digits. The reason for that is 2 to the 3 is 8. And so we only need 3 binary digits to represent an octal digit. 2 to the 4 is 16, which is why we need 4 binary digits to represent each one of our hexadecimal digits in our number. Okay, that's going to do it for our number systems. We went through base 2, base 8, which we didn't really talk that much about. It's not a very commonly used number base, although it is one of the powers of 2, so it does get used occasionally. We went through base 10, which is the one that we all are mostly familiar with now, decimal, and then base 16 hexadecimal, which is very commonly used also. My recommendation, make sure that you definitely understand binary. You already probably understand decimal, and make sure that you understand hexadecimal. Make sure that you can convert from one to another. And now we're going to move on to our next lecture, so I'll talk with you all then.